This is gonna blow your mind. The universe is a strange and mysterious place. It's a vast expanse filled with wonders and enigmas that boggle the mind and challenge our understanding. From the smallest particles to the largest galaxies, every corner of the cosmos holds secrets waiting to be uncovered. The more we learn about it, the stranger it seems. Each discovery opens up new questions, revealing layers of complexity that we never imagined. It's as if the universe is a grand puzzle, with each piece more intricate than the last. This is especially true in the realm of quantum physics, the study of the very, very small. Quantum physics delves into the behavior of particles at the atomic and subatomic levels, where the rules of classical physics no longer apply. Quantum physics governs the behavior of atoms and the particles within them. It's a world where particles can exist in multiple states at once, and where the act of observation can change the outcome of an experiment. It is a world where the familiar rules of classical physics no longer apply. Instead, we find a reality painted with probabilities and uncertainties, where nothing is set in stone and everything is in a state of flux. Instead, we find a reality painted with probabilities and uncertainties. Imagine a world where you can never know both the exact location and speed of a tiny particle. This is the essence of quantum mechanics. Imagine a world where you can never know both the exact location and speed of a tiny particle. This is the essence of quantum mechanics, a field that defies our everyday experiences and challenges our perceptions of reality. That's the bizarre reality described by Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. This principle tells us that the more precisely we know one property of a particle, such as its position, the less precisely we can know another property, such as its momentum. This principle tells us that the act of observing a quantum system inherently alters it. It's like trying to observe a delicate ecosystem without disturbing it. The very act of looking changes what you see. It's like trying to pinpoint the position of a soap bubble in a gentle breeze. The very act of looking at it changes its course. This inherent uncertainty might seem unsettling, but it's this very fuzziness that gives rise to the universe as we know it. This inherent uncertainty might seem unsettling, but it's this very fuzziness that gives rise to the universe as we know it. It's a universe built on possibilities where particles can be in multiple states at once, a concept known as superposition. It's a universe built on possibilities where particles can be in multiple states at once, a concept known as superposition. In this strange quantum world, particles can be here, there, and everywhere in between, all at the same time. It's a universe where things can pop in and out of existence, defying our everyday intuition. Particles can appear and disappear seemingly at random in a dance of creation and annihilation that underpins the fabric of reality. But perhaps the most mind-boggling aspect of quantum physics is its potential to explain the origin of the universe itself. How did something come from nothing? This question has puzzled scientists and philosophers for centuries. How did something come from nothing? This is where quantum cosmology steps in, offering tantalizing glimpses into the universe's first moments, a time when the entirety of space and time may have been compressed into an infinitesimally small point. This is where quantum cosmology steps in, offering tantalizing glimpses into the universe's first moments, a time when the entirety of space and time may have been compressed into an infinitesimally small point. From this singularity, the universe exploded into existence in a cataclysmic event known as the Big Bang. The Big Bang theory, supported by quantum mechanics, suggests that the universe began as a quantum fluctuation, a tiny blip in the fabric of space-time that rapidly expanded to form everything we see today. This idea challenges our understanding of cause and effect, suggesting that the universe itself is a product of quantum uncertainty. As we continue to explore the quantum realm, we uncover more about the fundamental nature of reality. Each discovery brings us closer to understanding the true nature of the universe, a place where uncertainty and possibility reign supreme. The universe is a strange and mysterious place indeed, but it's this very strangeness that makes it so endlessly fascinating. In the dance of particles and the play of probabilities, we find a cosmos that is as beautiful as it is bewildering, a universe built on uncertainty. And a special thanks to Thunderbird Perch for making this exploration possible. Stephen Hawking, a legendary figure in physics, dared to venture into the heart of black holes, those enigmatic regions of space where gravity is so intense that nothing, not even light, can escape. His work wasn't just about understanding these cosmic phenomena. It was about pushing the boundaries of human knowledge and challenging our perceptions of the universe. and the beginning of time. Hawking's theories took us back to the very dawn of existence, to moments so early in the universe's history that they defy conventional understanding. Hawking, using the language of mathematics, explored the universe's most extreme environments where gravity warps the fabric of space-time. His equations and theories provided a window into realms that were previously the domain of science fiction, and he did it all while facing the debilitating challenges of ALS. Despite his physical limitations, Hawking's mind soared to places few could imagine, proving that the power of intellect can transcend even the most severe physical constraints. One of Hawking's most significant contributions was his work on imaginary time. This concept, while abstract, has profound implications for our understanding of the universe. Now, imaginary time isn't some science fiction concept. It's a mathematical tool that allows physicists to navigate the complexities of the universe's origins. It's a mathematical tool that physicists use to grapple with the singularity at the Big Bang, a point where our current understanding of physics breaks down. By employing imaginary time, scientists can create models that bypass the singularity, offering a more coherent picture of the universe's birth. Imagine time not as a straight line but as a curved dimension, like the surface of a sphere. This analogy helps us grasp the idea that time could be finite yet unbounded, much like the surface of the Earth. This is the essence of imaginary time. It allows us to conceptualize a universe where the traditional boundaries of time and space are blurred, offering new insights into the nature of reality. It helps us visualize a universe without a defined beginning or end, a universe where time itself might loop back on itself. This cyclical view of time challenges our linear perception and opens up possibilities for understanding the cosmos in entirely new ways. Hawking's work, alongside other brilliant minds, opened up new ways of thinking about the universe's origin. His theories have inspired countless scientists to explore these ideas further, pushing the boundaries of what we know and what we can imagine. It hinted at a reality where the Big Bang might not have been the beginning but just a transition, a phase in an ongoing cycle of cosmic events. This perspective reshapes our understanding of the universe's history and its future, a point where our classical understanding of time and space cease to apply. In this view, the universe is a dynamic, ever-evolving entity with no clear start or finish, just an endless dance of creation and transformation. Lawrence Krauss, a renowned theoretical physicist, has made significant contributions to our understanding of the universe. His work often bridges the gap between complex scientific concepts and public understanding, making him a prominent figure in the field of cosmology. Krauss's ideas are not just theoretical musings, they are grounded in rigorous scientific research and have sparked widespread discussions and debates. And Alexander Vilenkin, a leading cosmologist, has also made groundbreaking contributions to our understanding of the cosmos. Vilenkin's work delves into the very fabric of space-time, exploring the origins and evolution of the universe. His theories have opened new avenues of thought and have been instrumental in shaping modern cosmological models. Both Krauss and Vilenkin have each proposed intriguing ideas about how the universe might have sprung from nothing. These ideas challenge our conventional understanding of existence and push the boundaries of what we consider possible. Their theories invite us to rethink the very nature of reality and our place within it. Their theories, deeply rooted in quantum mechanics, challenge our traditional notions of cause and effect, of beginnings and endings. Quantum mechanics, with its inherent uncertainties and probabilistic nature, provides a framework that allows for the possibility of the universe emerging from a state of nothingness. This concept is both fascinating and perplexing as it defies our everyday experiences and intuitions. Krauss, in his book A Universe from Nothing, argues that the laws of physics themselves could have bootstrapped the universe into existence. He posits that the universe could have arisen spontaneously from a quantum vacuum, a state that is far from empty. This vacuum is a seething, dynamic entity filled with virtual particles that constantly pop in and out of existence. He suggests that the quantum vacuum, often described as empty space, is actually teeming with virtual particles popping in and out of existence due to the uncertainty principle. This principle, a cornerstone of quantum mechanics, implies that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. This inherent uncertainty allows for the spontaneous creation of particles, which could have provided the initial conditions for the universe's birth. This constant bubbling of quantum activity could have, according to Krauss, provided the spark for the universe's birth. The idea that something as vast and complex as the universe could emerge from such seemingly chaotic and random processes is both awe-inspiring and humbling. It suggests that the universe is a product of the fundamental laws of nature, operating at their most basic level. Vilenkin, on the other hand, proposes a model called tunneling from nothing. This model is based on the principles of quantum mechanics and suggests a different pathway for the universe's emergence. Vilenkin's idea is that the universe began as a tiny, self-contained speck of space-time existing in a quantum state. This speck was not bound by the classical laws of physics, but was instead governed by the probabilistic nature of quantum mechanics. He suggests that the universe began as a tiny, self-contained speck of space-time existing in a quantum state. This speck, governed by the laws of quantum mechanics, could have then tunneled through a barrier of nothingness, expanding rapidly into the universe we observe today. This process, known as quantum tunneling, allows particles to pass through barriers that would be insurmountable according to classical physics. This speck, governed by the laws of quantum mechanics, could have then tunneled through a barrier of nothingness, expanding rapidly into the universe we observe today. The concept of tunneling from nothing is a profound and mind-bending idea, suggesting that the universe's birth was a quantum event, driven by the strange and counterintuitive rules of the quantum world. Both Krauss's and Vilenkin's theories offer compelling, albeit mind-bending explanations for how something could arise from nothing. These theories are not just abstract ideas, they are grounded in the mathematical framework of quantum mechanics and supported by observational evidence. They provide a glimpse into the possible mechanisms that could have given rise to the universe, challenging us to expand our understanding of reality. They highlight the profound implications of quantum mechanics on the grandest of scales, suggesting that the universe's origin might be a consequence of the inherent fuzziness and uncertainty that govern the quantum realm. These ideas not only deepen our understanding of the cosmos, but also inspire us to continue exploring the mysteries of the universe, driven by the curiosity and wonder that define the human spirit.